Hello everyone, good afternoon to all of you. So today we are going to discuss a very important topic of JEE and NEET, that is the nucleophilic substitution reactions. Among this we will be discussing today nucleophilic substitution unimolecular. So nucleophilic substitution reactions. There are many types of nucleophilic substitution reactions like SN1, that is nucleophilic substitution unimolecular, SN2 nucleophilic substitution bimolecular, SNI nucleophilic substitution intramolecular. Similarly SNNGP that is nucleophilic substitution neighboring group participation, as well as SN prime. So among these we will be discussing today only SN1 mechanism, that reaction, the factors affecting it, and few important things that are very beneficial for the students whenever it comes to solving the JEE and NEET question. So if I discuss about the SN1 reaction, what is SN1 reaction? It is a very simple reaction. It is called substitution nucleophilic unimolecular. So what is the meaning of substitution and nucleophilic? So first of all we should know what are the nucleophiles. So we can say that nucleophiles are nucleus loving species. Anything having we can say extra charge, or anything is electron rich or carrying negative charge, they all are called nucleophiles. Nucleophiles, or we can say them Lewis bases, they are also the nucleophiles. So what happens here? We are having Rx. On this Rx, if a nucleophile attacks, then we will get RNU plus X negative, where this X, it is called leaving group. What is happening here is that this nucleophile is substituting this X. X is halogen. So this is what is happening. This is what happening here is the nucleophilic substitution reactions. So unimolecular, why it is unimolecular? Because the rate determining step involves only one molecule. I'll explain later. So because its rate of reaction, its rate determining step involves only one molecule, or we can say that RDS is dependent only on one molecule, something like this. So this we will discuss in the next slide. For example, let us take the hydrolysis of alkyl halide. So what is happening here? We are having Rx. Let us take this R as tertiary carbon. Why? We will discuss in the factors why it is happening like this. Then we have to do the hydrolysis. This water molecule here is acting as solvent as well as the nucleophile. Okay, we can just write like this. So what happens here? ROH plus X negative. This is the nucleophilic substitution unimolecular. So this tertiary, I can take the examples as CH3, C, CH3, CH3. Here we have Cl. Now attack of nucleophile, that is H2O. What we will get? CH3, C, CH3, CH3 and OH. So this is how this nucleophilic substitution unimolecular reaction proceeds. Now if we discuss about its mechanism, sorry, it is a two-step reaction. In this step 1, first of all, what happens, like we had taken CH3 thrice, CCl, this CCl bond gets dissociated. In the first step, CCl bond gets dissociated, hence generating a stable carbocation. So this is happening like this. Now this step 1, this step is also rate determining step. Why? Because the bond dissociation is happening. Always remember, my dear friends, that rate determining step is something which takes place while bond is dissociating. When the bond dissociates, now this dissociation of C and Cl bond will determine how fast this reaction will go or how slow this reaction will go. Now in this rate determining step, only one molecule is participating. This molecule is participating here. Only this molecule is participating. That is the reason why we call it nucleophilic substitution unimolecular. Unimolecular. So if I write its rate, then I can say rate is directly proportional to concentration of Rx. Suppose I take rate directly proportional to concentration of Rx as well as nucleophile. So this becomes the first order reaction and it becomes second order reaction. Why? Because the nucleophile as well as alkyl halide both are participating. But in this topic that we are discussing today, we are discussing only nucleophilic unimolecular. That is the first order reaction. Only one molecule, that is Rx, is participating in this reaction. Okay, so this is the case. So in the second step, what happens? Step 2, this carbocation is attacked by water or nucleophile, we can say. So what happens here? CH3 thrice carbon. Now this oxygen is having lone pair and this carbon is having positive charge. This carbocation is electron deficient. This water molecule, it is electron rich. Remember, I am repeating again. This water molecule is acting as solvent as well as the nucleophile in this reaction. So obviously this carbon will be forming a bond with the lone pairs, with the help of lone pairs with this water molecule. So we will get COH. As oxygen has donated its lone pair, it will has the positive charge. So it will have the positive charge. And other water molecules again comes here. This pair of electron will be shifted by oxygen and it will go outside. So whatever we are getting is, in the last step we will be getting CH3 thrice COH. This is a mechanism. This is a two-step mechanism that SN1 reaction follows. Okay. So now the question is, why carbocation in this case forms bond with water? Why not with Cl negative again? This is the thing. So this is decided by the solvent, nature of solvent. Either you use polar protic solvent or you use polar aprotic solvent. So it is determined by the same thing. Okay. So we will discuss its answer. We will give in the factors. While discussing the factors, we will discuss this thing. Okay. So earlier we were discussing about the rate. So here the rate of reaction is directly proportional to concentration of Rx and it is also the first order reaction. Only one molecule is participating in the reaction, so that is why it is called unimolecular reaction. Also, what we can say, suppose I have taken what will happen if the concentration of Rx is doubled. If the concentration of Rs is doubled and concentration of nucleophile is also doubled, what will be the rate of reaction? Will it go 2 times? Will it go 4 times? Will it go 8 times? Or will it remain the same? So as we know, the rate of reaction is directly proportional to the concentration of Rx It is independent of nucleophile. So nucleophile's concentration doesn't matter how much concentration you can take for the nucleophile. For this Rx, if I am taking its concentration as double, so the rate will also become double. So the double will be the answer, or we can say the rate of reaction will also be doubled in this case. So this is how the rate of reaction is dependent on the concentration of alkyl halide. Okay, so sometimes, or we can say that this SN1 mechanism proceeds according to stability of carbocation. For this stability of carbocation, we know the sequence: tertiary, secondary, primary, and then methyl carbocation. They are important for us. Okay, so according to the stabilities, the rate of reaction proceeds here. Also, there are other variable factors. We can also say that rearrangement of carbocation can also take place. Rearrangement of carbocation can also take place with the help of hydride shift, with the help of methyl shift, or with the help of phenyl shift. So these three type of shifts we can also carry out while we are discussing the stability of carbocation. Okay, so now in this case we had a question: why carbocation forms bond with water, not with Cl negative? Okay, so let us discuss. C positive bonds with water, C positive do not bonds with Cl negative again. Now what happens here? In this case what we are using is PPS. What is that? It is polar protic solvent. What is this polar protic solvent? This polar means anything having charges, partial charges. Protic means anything containing protons, and solvent, we know that in solvent is the medium in which solute is dissolved. Okay, so what happens here? Suppose we have got this C positive here. It is tertiary carbocation, and we are having Cl negative. Now it has become the nucleophile. It has become the electrophile. Water molecule we have is electron rich. So if you imagine, this Cl negative is surrounded by hydrogen. Why? Because this hydrogen carries delta positive charge. Crowding takes place. Hydrogen, oxygen, hydrogen, again delta positive, delta positive. Similar things again happens like this: hydrogen, oxygen, hydrogen, like this. Delta positive, delta positive, delta positive, delta positive. Now you people explain me, tell me that how this Cl negative surrounded by various solvent molecules will again be able to make a bond with the same carbocation. This happens, this is the effect of solvent in this case. Two type of solvents we use in the nucleophilic substitution reactions. One is the polar protic solvent, the another one are the polar aprotic solvent. So here we are using polar protic. This polar protic solvent surrounds the leaving group. Hence, if its mobility becomes 0, this chloride ion is now not able to make a bond, back bond with the carbocation. So the available option for this carbocation is water molecule. So hence we get the desired product in this case. Okay. So next, we were talking about the stability of carbocation. Carbocation stability. Let us discuss this thing with a question. Let us take CH2Cl, CCCl, C. Okay. Then let us take C and Cl, and the last one let us take CH2 double bond CH, CH2 and Cl. Now if I take A, B, C, D. Now you people tell me which carbocation will be the most stable. Now if we look closely towards this compound, this bond will be dissociated from here. It will become benzyl carbocation. Benzyl carbocation is stabilized by resonance. Okay. Here if you dissociate it, it will become tertiary carbocation. This tertiary carbocation will be stabilized by hyperconjugation. Here the carbocation is benzyl, means this is stabilized by resonance plus hyperconjugation. Here the carbocation will be stabilized by resonance. Now this C option, we have two factors involved in the stability of carbocation. Which are the two factors? One is the resonance, the other one is the hyperconjugation. Hence C will be most stable carbocation and it will gives readily the SN1 reaction. Similarly, we can take another example. I hope it is clear to you. Similarly, we can take another example like this. Here, let us take bromine. Br and Br here. Okay. So, it is A, B, C. Now, if you look clearly in this case, let us take this color. It will be a carbocation. It is resonance stabilized. Why? Because it is allyl carbon. Dissociate this bond, it will become tertiary, hyperconjugation is there, and it will become secondary. So clearly, always remember the stability of tertiary carbocation is more than allyl carbocation. There are few factors that we will discuss in the detail sometimes. So the order will become B, A and C. That means B will readily give SN1 mechanism. Secondary carbocation can give both SN1 as well as SN2 depending upon the solvent and some other factors. So for secondary carbocation, we are not sure which type of reaction it will give. It depends upon the availability of this solvent. Okay. Next factor, we have a CCl bond and a CO bond. The question was the same. Why carbon is not forming bond back with the Cl? Why it is forming bond with the nucleophile? In CCl bond, there is the overlapping of 2p and 3p orbital. Here is overlapping of 2p and 2p orbital. So anyone who knows chemical bonding, it is clear that this CO forms a strong bond. Also, it is exothermic in nature. Exothermic means the energy is liberated, energy is lost, and the product formed is more stable in this case. Next thing that is very important from SN1 and SN2 mechanism, that is its stereochemistry. Stereochemistry. So let us start directly with the carbocation like this, this and this. Because it is sp2 hybridized carbon, the leaving group has already left the carbon, and this carbon present here is sp2 hybridized. So the vacant orbital is like this. Okay. So here two cases are possible. Suppose the chloride which has left is present like this. It was present on the upper side. So if the nucleophiles attacks from the upper side, we will get something like this. Nucleophile, if it attacks from this side, sometimes people say front side attack, back side attack, sometimes people say from the both sides it is attacking on the left hand side, right hand side. So we can say from whichever orbital the chloride has left, if the nucleophile is attached from the same side or the nucleophile is attached from the other side. If nucleophile is attached from the same side, retention occurs here. Retention means, I will tell you, retention occurs here, and if it attacks on the other side, inversion takes place. That means if this molecule was having R rectus, then it will become R after the bond formation. But if it was R and the bond is found from the lower side, it will become S sinister. This is called inversion of the molecule. Why it is happening? Now, which product will be more, retention or inversion? In NCERT and so many books it is written that the product formed from here, that is racemic mixture. Racemic mixture, that means retention and inversion, they both are present 50%. But in many books which are written by foreign authors, they have suggested that inversion is always greater than retention. It is an important point. Why it is happening so? Suppose chloride bond is dissociated from here. So that means if carbocation is present, this chloride ion might be revolving somewhere around this corner. So if this nucleophile is attacking from this side, this chloride will be revolving somewhere here. Ultimately, this chloride will be repelling this nucleus. So the product, the amount of product from the same side will be less. Retention is less. And if it comes from this side, it is very easy to attack from the downside because there is no chloride ion revolving around here. So that's why inversion is mostly greater than retention in this case. Okay, I hope this stereochemistry is clear to you. Next we have is the nature of leaving group. Nature of leaving group. If the leaving group leaves early, product reaction will be fast. Ri, R, Br, RCl and Rf. If we talk about in the simple words, here the overlapping is 2p, 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 3p, 2p, 4p, 2p and 5p. The weakest bond is present in Ri, alkyl iodide, hence this Ri bond will be dissociated easily. So iodide ion will be liberated very easily, then bromide, then chloride and then fluoride ion. Okay. So next, the last point we are having is the nature of solvent. Nature of solvent. Now the solvent here we need is polar protic solvent. This polar protic solvent must have a proton and it should have the polar nature. CX bond dissociates. This CX bond dissociates. Better the solvent, more is SN1 reaction. Suppose I am taking the example H2O, C2H5OH and also I am taking CH3COOH. Now the dielectric constant for water is 80, it is 35 and it is 5. What is the meaning of dielectric constant? In simple words we can say the force applied to break this CX bond. The force applied to break this CX bond is called dielectric constant. So water, it gives the best SN1 reactions here. So this is the case. And one more thing I want to explain, that is the stability of carbocation. Suppose we are having something like this C, C, C. Here we are having Br and the another we are having CH3, H, C and Br. Okay. So something like happening like this. So in this case, bond will be dissociated from here. So it will form CH3, C positive, CH3 thrice. But in this case, we will get the primary carbocation. So what we can do from here, just shift this hydride to here in this position. So what you will get C, C, CH3. This C is like same, C is same, and this hydride is now shifted to this position and carbocation is formed at this position. Hence, the primary carbocation is changed to tertiary carbocation. This is called tertiary. This is called hydride shift or rearrangement of carbocations, which helps in proceeding this type of reaction. So this is all about the SN1 mechanism. Let us discuss a previous year question. Thank you very much.